There's one simple hearing hack anyone can use to improve their hearing almost overnight. Did you know that hearing impairment?
One of the most fundamental physics facts is that the speed of light in a vacuum is constant for all observers. But can we really be sure that the speed of light wasn't different in the past, or perhaps in other parts of the universe? In fact, variable speed of light theories have long been used to try to explain everything from dark energy to gravity itself. So let's explore how constant this fundamental constant really is. Speed is relative. Drop your smoothie on a train and it appears to fall straight down. But to me, standing on the platform, the smoothie falls diagonally, apparently boosted by the speed of the train. But shine a laser beam from that train and everyone observes the same speed, 299,792,458 meters per second in a vacuum, no matter their relative speeds. The invariance of the speed of light is more precisely described by something called Lorentz invariance, and it's the founding axiom of special relativity. Einstein realized that our measurements of distance and time have to be relative to the observer. They have to shift to keep the speed of light the same for everyone. This same axiom is also fundamental to general relativity, in which gravity is interpreted as a warping of the fabric of spacetime. Both special and general relativity have been tested with extreme care and precision over and have never failed. More to the point, the speed of light has been measured in different reference frames, and its invariance holds down to the exquisite precision of current methods. That said, we scientists are supposed to remain simultaneously skeptical and open-minded, somehow applying both mindsets to both old and new theories. So, in that spirit, let's ask whether the speed of light is really invariant. For example, could it change over time or be different in different parts of the universe? There are some who believe that the very effects that relativity predicts are due to the speed of light changing, not due to changes in space and time themselves. Now, before I start talking about what it means for the speed of light to change, I want to make it clear why many and perhaps most physicists think that it's not only impossible, but it's not even meaningful to think about a variable speed of light. The speed of light isn't really about light. It's the speed of any massless particle and also the maximum speed that information can travel. It's the speed of causality. It's the rate at which one point in space can communicate with its neighbors, assuming no impediments. So to change the speed of light, we'd need to change something pretty fundamental about the universe, the connection between space and time. We measure speed in terms of the amount of distance traveled per unit of time, whether that's miles per hour or meters per second. Changing the speed of light means changing the number of meters it can travel every second. The problem with this is that our very definition of meters and of seconds are tied to the speed of light. We can think of the meter as the distance light travels in 1/300 million seconds, or we can think of the second as how long it takes light to travel 300 million meters. Einstein said that time is what clocks measure, which we can interpret as meaning that time is a measure of the rate of change of the universe. One of Einstein's thought experiments was the photon clock, in which he imagined a photon bouncing between two mirrors, and each two-way trip indicates a tick of the clock. So what happens if we slow the speed of light? The clock ticks more slowly, which means time slows. Now, real clocks are made of gears or electronics, which are made of atoms, which are made of various quantum oscillations bound up in ways analogous to the photon clock, whether electrons communicating virtual photons with a nucleus or quarks exchanging gluons in that nucleus. This argument applies for any object with mass. The speed of light dictates the rate of internal change, which determines the rate of the flow of time for all matter. So, if slowing light also slows time, would we even notice? Not according to special relativity, in which space and time are fundamentally coupled, two sides of the same coin. Changing the speed of light slows time, and moving the mirrors further apart also slows time. In this picture, distance, time, and the speed of light scale together. So on our scale, there's no observable effect. The speed of light is just the unit conversion factor between our arbitrary choices of spatial and temporal units. The only way for a change in the speed of light to do anything is if time and space both have their own fundamental units that are independent of each other. If there's a basic smallest unit of space and a smallest unit of time, and these don't depend on each other, then maybe changing the speed of light would change the relationship between space and time, at least on the quantum scale. So let's imagine this is possible and explore the consequences. The first real variable speed of light, or VSL theory, was proposed by Robert Dicke back in 1957. Dicke was a brilliant physicist and astronomer with wide-ranging contributions, so we should at least pay attention to his musings. Dicke wondered if gravitational fields might not be due to the bending of space-time, but instead due to the speed of light slowing down near massive objects. Remember that light changes its direction as it moves into a medium where its speed is lower. That's exactly how lenses work. So why not gravity too? And we know that time does tick slower in a gravitational field, and we now know that slowing the speed of light should slow time. It seems like a variable speed of light could be an elegant alternative hypothesis, no? No. Back in 1957, there were only a few successful tests of general relativity, and some of those were consistent with either space-time curvature or a changing speed of light. But nowadays, we know that space-time itself must be dynamic. We've measured how rotating masses drag space around and how colliding black holes generate gravitational waves, none of which work with the variable speed of light interpretation. Dicke's idea was intriguing, but it doesn't stand up to the latest evidence. And given that evidence, Dicke himself would surely agree. Okay, so maybe a variable speed of light doesn't explain all of gravity, but could it still play a part? There's one weird fact about our universe that could possibly be explained by this idea. If we look at the edge of the observable universe in that direction, we see a warm, smooth gas that existed before any stars or galaxies formed. We see exactly the same in that direction or that or that. The universe at early times was extremely homogeneous, almost the same density and temperature everywhere. That tells us that at some point in that distant past, all of that material had to have been in contact in order to distribute energy and settle into the same state. But the problem is, based on the observed rate of expansion of the universe, there just wasn't enough time since the Big Bang for those regions to have communicated with each other. We've talked about this so-called horizon problem previously, along with the mainstream solution of cosmic inflation. Inflation hypothesizes that at some very early time, those distant regions were in causal contact with each other, enabling them to share energy at regular light speed and reach the same temperature. But then, the universe underwent a period of extremely rapid expansion, much faster than the speed of light, before slowing dramatically. This threw apart regions that were once close enough to be in thermal equilibrium so far apart that it appears now that they could never have been. But there is another way to bring those distant points into causal contact, and that's by having light move faster in the past. This could have kept the early universe connected as it expanded and reached uniformity. Then, if light slowed down to the current much slower speed, distant regions would seem causally disconnected. And if this story is right, it could even be that the speed of light has been gently decreasing ever since. It's been suggested that this could explain why many galaxies appear to be accelerating away from us. Since light is supposedly becoming slower, it's taking longer and longer for their light to reach us, giving the appearance that they are accelerating away from us. That may sound good, but variable speed of light theories don't have a good explanation for why light speed would change in the very particular way needed to mimic both inflation and dark energy. Cosmic inflation seems a little cleaner and is certainly better accepted. The first effort to explain the horizon problem with a variable speed of light theory was by John Moffat in 1992. He proposed that the speed of light may have been 10 to the power of 30 meters per second in the early universe. Moffat lays out some substantial theoretical work involving symmetry breaking, analogous to the one that separated the electromagnetic and weak forces, but in this case, the broken symmetry was Lorentz invariance. Moffat's theory preserved Lorentz invariance on relatively small scales, like across the galaxy, but allowed it to vary over cosmological distances and times. Another similar idea came from Andreas Albrecht and João Magejo. And yet another VSL model depends on the energy of light. Higher energy photons would move faster. Perhaps then the ultra-high energy photons near the Big Bang didn't travel fast enough to connect distant points of the universe. Then, as the universe cooled, those high-energy photons became rare, and so light slowed down. Now, we have absolutely never observed speed differences for lights of different energies at any energy that we've detected. And that includes comparing the arrival times of high-energy gamma-ray light from gamma-ray bursts with the arrival times of lower-energy light from the same explosions. But maybe the effect only kicks in at the really ridiculously high energies near the Big Bang. These are fun ideas, but are they testable given that VSL theories predict the same thing as more standard ideas of general relativity? Well, there's another way to look for changes in the speed of light, and that's via its effects on physics. C appears everywhere in our laws of physics. For example, in the fine structure constant, which defines the strength of electromagnetism. The formula for alpha includes the charge of the electron, the electric permittivity of the vacuum, Planck's constant, and the speed of light. We've talked about this important constant of nature in the past, and even about whether it may have changed over time. Well, if the speed of light has changed, then you'd expect the fine structure constant to change with it. And guess what? There is no evidence for such a change, and you can see our previous episode for that lack of evidence. None of this proves that the speed of light has never varied. It just says that it can't have varied much over the past billions of years. But the real challenge for VSL theories is how they seem to break physics. All VSL theories break Lorentz invariance, and Lorentz invariance seems pretty important for the universe to make sense. Remember the example about the smoothie from the beginning of this video? In that example, you and I had a different interpretation of the same event, and yet we would both agree on every aspect that mattered, like the fact that the smoothie hits the floor at a particular location, or that it hits the floor after it's dropped rather than before it's dropped. The basic self-consistency of the universe and the causal ordering of events is ensured under Lorentz invariance. Break it, and it's pretty easy to come up with nonsensical scenarios in which different observers have irreconcilable disagreements about the outcomes of events. A variable speed of light also breaks the fundamental charge parity time, or CPT, symmetry of the universe, in that the laws of physics would look fundamentally different depending on which direction in time you're moving. We've discussed CPT symmetry before, and this is also problematic because CPT symmetry is believed to be truly fundamental, and we have no other evidence of it breaking. There are some ways around some of these objections. For example, you could imagine that the change in the speed of light is not exactly fundamental, but more akin to how that speed changes in a dense medium like water. So what if the refractive index of the universe changed over time? Well, that supposed increase in the thickness of the vacuum would have to be pretty enormous in order to slow light by the factor of 10 to the power of 22 needed to solve the horizon problem. And that change would appear to affect all light speed waves equally, all frequencies of light, as well as gravitational waves. Regular materials don't behave like this. Still, it is a sort of way out. And there are some other narrow paths through the dense network of refutations of VSL theories. However, you need to be pretty committed to these ideas to find these ways out. Currently, there is no evidence that the speed of light varies in a fundamental way, and it may be that it's not even a meaningful concept. Although that latter point depends on an understanding of the quantum nature of space and time and their relationship to each other that we don't yet have. It's absolutely worth going back and questioning the founding axioms of even our most successful theories, as long as we keep in mind that any new theory is going to have to do just as well or better than the old one in all of its predictions. And that's a tall order when you're trying to break relativity, which has such deep internal consistency and is so powerfully predictive. But relativity is not the final theory due to its clash with quantum mechanics. So let's keep questioning it, including whether the cosmic speed limit is fixed or we can somehow change how fast information travels through space-time. So we missed a few comment responses recently. Actually, we missed 6. It's my fault. There's been a lot going on, including too much travel. And these responses actually take a lot of thought on account of your really, really good questions. So today, we're going to go back and do responses for a selection of the missed episodes. We'll catch up further on future episodes. We'll do one comment from each of these, but we're going to do each of those very fully, and we'll also do them completely out of order. We have the episode on superfluids, then the one about turning the sun into a spaceship, and the one about detecting planet-sized spaceships using LIGO, and finally the one about how terrible or awesome the next nearby supernova is likely to be. But before we jump into that, I also need to note a correction for our episode on the model of the interior of the proton. We talked about the important contributions of Stan Brodsky from the Stanford Linear Accelerator, but we managed to use a picture of the wrong Stan Brodsky. This is the Stan Brodsky we meant to shout out. Apologies to both Stans. Okay, finally to comments, and starting with our episode on superfluids. Here's an insightful comment from Martin Stent 5339, who suggests that it would be impossible to stir a superfluid into a vortex because the fluid would just slip around the spoon rather than being pushed into a flow. So there's some good intuition here, but the conclusion is not quite right. The spoon does impart energy to the fluid. After all, the helium atoms have to move if they can't pass through the spoon. And those moving atoms push on other atoms, so you do get a new flow, which can translate to the rotation of the vortex if the spoon is stirring. The point of the superfluid is that superfluids love moving in unison, in streamlined flows, and that vortex is such a flow. What superfluids hate is atom-to-atom level exchanges of random chunks of energy. They hate dissipative interactions which translate to friction, heat buildup, and viscous movement. However, as I mentioned in that video, it is possible to induce a sort of emergent viscosity by creating tiny vortices in the superfluid, which then interact with each other in a way that disrupts viscous flow. That happens due to interaction with a non-perfectly smooth container wall, but stirring with a spoon should also do some of that. Let's move on to the episode where we described ways to move the entire sun to a different galactic orbit. SABR MAT 2010 has a major problem with the claim that the planets in the star's orbit would just come along for the ride when thrusting a star, because it would actually create a momentary imbalance in the gravitational field that could destabilize carefully tuned orbital resonances. So you are absolutely right that moving the sun wouldn't quite drag the planets along with literally zero effect. Moving the sun with a very tiny amount changes the center of mass of the solar system, and the orbits would have to shift a little bit. But if that change was tiny, they'd quickly find new stable orbits not much different to their last, and still close to resonance. If the sun keeps moving, but moves slowly compared to the amount of time it takes to recover orbital resonance, then the sun could be moved without disrupting the planets. But if you try to move the sun too quickly, then yeah, you could break the solar system. Fortunately, the proposed methods do move the sun very slowly, and I believe that's even the case for the relatively rapid Kaplan thruster. While we're on gigantic spacecraft, let's move on to the episode on detecting gigantic spacecraft from the gravitational radiation that they emit when accelerating. Brothermine 2292 points out that Ramacraft aren't the only linear accelerators that would emit detectable gravitational waves. So would the very rare head-on collisions between two black holes. And that is correct. We did very briefly mention natural causes in that video, but to elaborate, a head-on collision between any compact body, black hole, neutron star, perhaps even white dwarfs, would cause both objects to massively decelerate in a straight line, resulting in linear gravitational waves that could be detectable. For the black hole, there should be a very weird but modelable gravitational wave ring down as the two fell together again. For non-black holes, there should be a really clear electromagnetic signature, so hopefully we can distinguish these cases from aliens. And then there's the episode where we talked about the prospects of Betelgeuse going supernova and when the next supernova might be and what it might do to us. E.T. Lee DB6CN points out that a portion of Earth will be completely shadowed from the supernova depending on the supernova's location on the sky. So while it is true that being on the other side of the planet would shield you from the worst of the actual immediate radiation from the supernova blast, for most death by supernova scenarios, it's not the direct irradiation that gets you. The most likely killer is due to the ozone layer being depleted. Even if that happens only on one side of the planet, the effect quickly becomes global with atmospheric mixing. There's also the fringe case where a supernova goes off while you're in a region of the galaxy with relatively high gas abundance, which will then irradiate the entire planet in all directions with X-rays for a very long time. But yeah, maybe if you have a well-stocked bunker and happen to be antipodal to a very nearby supernova, you get to emerge years later and really enjoy the post-apocalypse. And by that time, I might have caught up on all of the missed comment responses, so it's a double win, really.
I've got home internet from T-Mobile. It only costs $50 at T-Mobile. Just one cord to set up. Say goodbye to that.
Home internet from T-Mobile, just $50 a month.
Close your eyes and imagine yourself within a supervoid. Darkness envelops you, holding you captive and isolated. With your eyes, even with any amateur telescope, you see nothing. No stars, no hint of the fuzzy smudges we now know as our own neighboring galaxies. To you, the universe is empty. The Boötes Void is a spherical region 330 million light-years across, approximately 0.2% the diameter of the entire observable universe. The Milky Way could fit inside it millions of times over, and yet within a volume of about 1 million cubic megaparsecs, where there should be thousands of galaxies, we have observed only 60. Spiral galaxies, blue with the light of new star formation. To quote astronomer Greg Aldering, if the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Indeed, were the Earth to rest on one edge of this void, observers on the other side would only now be receiving light from a time when amphibians dominated the Earth, before even the age of the dinosaurs. Even now, we do not fully understand how such a void came to be. The age of the universe sets a limit for the maximum size of any structure, galaxy clusters, and indeed the voids in between. There should be no single structure in the universe that is already greater than tens of millions of light-years across. The Great Nothing, as the void is known, shatters this limit. Though its absence of structure does give us an insight into the growth of structure at the earliest of times. The few galaxies observed within the void following a tube shape, perhaps the crumbled remnants of a wall between two voids. Individually, these voids would each fit within the growth limit, but together they form a supervoid. And so, even here, in the Great Nothing, one of the darkest places in the universe, there is the light of galaxies, unveiling their secrets to us through the visible spectrum. To find true darkness, we will have to look further than even the Boötes Void. Further back in time. We can only find complete oblivion in the time before stars and galaxies and planets existed, forebodingly known as the Cosmic Dark Ages. Here, the darkness was total and long-lived. Although for about 200 million years after the Big Bang, the universe contained a variety of ingredients that could produce the first stars, none formed. There was no visible light at all. But why was the cosmos dark for so long? What does this mean for the stars and galaxies we see around us today? And how can we possibly hope to shed any light on an era when there was only darkness? In 1543, Nicholas Copernicus showed the Earth isn't the center of the solar system. In the 1920s, Jan Oort discovered the Sun wasn't in the center of our galaxy, and in that same decade, Hubble discovered our galaxy was just one of countless others. Cosmologically, we aren't the center of anything, and that is a sobering realization. This video has been kindly sponsored by BetterHelp, and they are here to help you through life's many realizations. With BetterHelp, you can tap into a network of over 30,000 licensed and experienced therapists who can help you with a wide range of issues. You can then talk to your therapist however you feel comfortable, whether it's via text, chat, phone, or video call. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but with a therapist who is custom-picked for you, with more scheduling flexibility and a more affordable price. So, get 10% off your first month at betterhelp.com/HOTU, and I've also linked them below in the description. Thanks to BetterHelp for supporting educational content on YouTube. In 1995, the then director of the Hubble Space Telescope, Bob Williams, had ring-fenced some personal observing time. He was the envy of the scientific world, holding precious hours on the world's greatest telescope, able to look at anything he wanted. At the time, Hubble was in the spotlight, but not for the right reasons, having used up billions of dollars of public funds only to require a crewed space mission to correct a near-fatal flaw in the system's optics. The mirror, which reflects gathered light into the instruments, needed to be extraordinarily smooth in order for the image to be in focus. Hubble's mirror was very smooth indeed, but the first images had been disappointingly blurry, a devastating blow to the intended science aims of the mission. It was determined that the mirror had an aberration less than a 50th of the width of a human hair that was causing the incoming rays of light to focus at different points, clouding our view of the cosmos. For most space missions, this would have been fatal, but Hubble was in low Earth orbit, making a repair mission not unrealistic. Astronauts installed several clever adaptations and replacements, correcting Hubble's eyesight to perfection. But now, Williams was under pressure to produce something of worth, something that would dispel the naysayers in politics, press, and even within the corridors of NASA. And so he decided to look at nothing. Against the counsel of his colleagues, Williams and his students steered the eye of the billion-dollar machinery such that it looked past the planets, sidestepped the stars, and away from the galaxies. Hubble instead settled its sights on a tiny patch of sky, only 1/30th the diameter of the Moon. And there it stared for 10 whole days. To our eyes and any other telescope that had come before, the patch was barren of structure. But this technology was a giant leap forward in astronomy, and the fine resolution and sensitivity of the Hubble Space Telescope revealed shapes in the darkness. Over a long exposure, the new Hubble could slowly gather photons coming from the farthest and faintest objects in the universe, and distant galaxies of every size, shape, and color emerged from the darkness. We now know this as the Hubble Deep Field, one of the most iconic images in astronomy. As with any photograph, this image is a 2D projection of a 3D landscape. Galaxies far removed in distance appear to be neighbors. It is also a projection of time. Photons from the farther galaxies have traveled for longer, and so we see those galaxies as they were farther back in time. Galaxies can even appear to be colliding when they existed as pictured billions of years apart. To understand why, let us consider the observable universe as constructed of a series of shells around us. The shell closest to us is easy to observe because the light travels to our telescopes almost instantaneously. Light from the Sun takes about 8 minutes to arrive to Earth. Move a shell outwards, perhaps to our nearest neighboring galaxy Andromeda, and from here, the light we see today has taken 2.5 million years to get to us. Released when one of humanity's earliest ancestors, Homo habilis, walked the Earth. We see Andromeda as it was 2.5 million years ago. This may be a long time for us, but it is still a short time in terms of the cosmological timeline, 13.8 billion years. As we consider the light from even farther shells, the photons we receive get progressively more ancient, and so we can see further back in time. And so with Hubble, we could finally observe light from galaxies as they were only hundreds of millions of years after the Big Bang. So faint and poorly resolved that they are mere red smudges in the sky, just as our closest galaxies were once smudges on the sky for the astronomers of the last century and before. We now have the means to pick apart the light that we observe, working out the composition of that galaxy and comparing known element markers to work out the distance to and age of the galaxies we see. This method uses the same principle that causes a fire engine siren to change pitch as it approaches and passes you on the street. As the fire engine approaches, the wavefronts of sound pile up, and we perceive a sound of shorter wavelength or higher frequency. Conversely, as the fire engine recedes, the wavefronts are increasingly spaced out, and we hear a lower pitch. The inherent siren pitch remains the same, but it is the relative movement between the source and the listener that causes a shift. Now imagine a galaxy as our siren, except instead of listening for the sound, we observe the siren light. This light is a specific color, blue, and does not change. As the galaxy recedes from us, however, the light wavefronts stretch out, and we observe a longer wavelength light. The siren gets redder. We call this shifting of the light spectrum redshift. Certain chemical elements are natural siren lights in the spectrum, producing a clear emission line at a known frequency. By measuring how much that line has shifted in a galaxy's spectrum, we can calculate the speed at which it is traveling away from us. Edwin Hubble, the famous astronomer for whom the telescope was named, observed that the further the galaxy, the faster it appeared to be traveling away, a keystone of the Big Bang theory. As a rule of thumb, the oldest light is the most redshifted. In this way, we prize apart the thousands of galaxies that appear tangled in the deep field images, and brush away layers of young galaxies until we are left with only the oldest, the first of their kind. The latest deep field image from the James Webb Space Telescope covers the area of just a grain of sand in the sky, and yet still thousands of galaxies emerged from the darkness, pushing back the cosmic frontier to only a few hundred millions of years after the Big Bang. We are finally reaching a time in the universe where there was no visible light at all, a time that even Webb is blind to. The frontier of the first stars. But does this mean we can go no further? Are we forever closed off from the darkness that came before?
Delicious fresh baked taste straight from your oven always wins. It's not delivery, it's DiGiorno.
In the beginning, light ruled the universe. The energy density of radiation far outweighed the energy density of matter, and interactions between the two were commonplace. So much so that photons of light quickly broke apart any atoms that formed, and as a result, the photons could not travel freely in this superhot, dense plasma of matter. This soon changed, however. While both densities reduced as the volume of the universe increased, radiation fell faster because of an extra factor: the stretching of light into longer wavelengths as the universe expanded and lower equivalent temperatures, cosmological redshift. After 380,000 years of expansion, the energy density of radiation had fallen below that of matter, and the dominion of light in the cosmos was long over. The temperature of the plasma had in fact cooled to such an extent that atomic nuclei could now reliably combine with electrons into simple atoms. Though light was now no longer the dominant force in the universe, there was an upside. The creation of atoms now meant photons had space to travel, having their paths diverted only occasionally through interactions with matter. But what would you have actually been able to see? The answer is hard to know for certain, but we can estimate what the universe would have looked like. The radiation at the point of recombination emitted as a black body, an object that emits radiation across wavelengths with a predictable shape, as long as you know its temperature. To an onlooker, the universe would have seemed to have a warm orange glow. Over the next few 100 million years, as the universe expanded further, the dropping temperatures led that glow to redden with time. Finally, it cooled such that there was no longer radiation emitted in the visible part of the electromagnetic spectrum at all. The embers of the Big Bang faded entirely into the infrared, microwave, and radio wavelengths. Darkness fell. In the midst of the black, however, all was not quiet. For another kind of matter was created in the Big Bang, a kind of matter that is still mysterious to us today. Dark matter. In the 1960s, scientists Kent Ford and Vera Rubin measured the orbital velocities of stars in spiral galaxies and found that something didn't add up. Orbital velocity, the speeds at which stars orbit a galaxy, is a fine balance. Too slow and gravity causes the star to spiral inwards. Too fast and the star overcomes gravity and flies out of orbit. Ford and Rubin carefully estimated the stellar mass and hence gravitational pull of a variety of galaxies and found that the stars were simply moving far too fast. Observation after observation pointed to an uncomfortable truth. There must be a hidden component of mass keeping them in orbit. And that hidden mass was known as dark matter. Calculations show that this dark matter makes up 4/5 of all matter in the universe, and yet it still evades our direct detection and capture today. The matter we see around us interacts with the universe both gravitationally and electromagnetically. Dark matter, in contrast, only interacts with the gravitational field. It cannot absorb or emit photons and so has no imprint on a spectrum in the same way chemical elements do. It does possess a gravitational pull, however, and so high-density areas of dark matter can grow and collapse through accretion, but only up to a certain point. And this is key. There can be no stars or planets made of dark matter. As a cloud of matter collapses, the pressure of the particles in the cloud fights back. Pressure is linked to temperature. The denser the particles, the hotter they are, and the more kinetic energy they have to more effectively create an outward-acting pressure force. Normal matter can convert thermal and kinetic energy into electromagnetic radiation via the excitation of electrons in colliding atoms. The atoms move apart at a slower pace, and when the electrons naturally return to their ground states, they emit photons, which carry away the parcel of energy from the cloud. The pressure is reduced permanently. But dark matter does not interact electromagnetically and so cannot emit photons. There is no escape valve. This means that once the outward thermal pressure of the system balances the inwards gravitational pressure, the collapse is simply halted. And so instead, dark matter collapses into filaments, connecting at their densest points into halos. Unable to emit light, our Big Bang observer could not see this vast background web of dark matter behind the uniform orange or red glow of the gas. Even in the total darkness that followed as the radiation shifted out of the visible, the dark matter remained hidden. For close to 200 million years, this remained the state of play, a web of dark matter that was doomed to darkness forever and a mist of gas too dilute to ignite fusion. And so, how could the universe ever form a star to break the impasse? And hidden as the evidence is in the total darkness at the beginning of time, how could we ever know what happened? On the 6th of May, 1937, flames viciously engulfed the German airship Hindenburg as it attempted to dock with its mooring mast in New Jersey. Bystanders could only look on in horror. Pride of the fleet, the ship regularly carried passengers across the Atlantic Ocean at a stately 80 miles per hour. This journey had been no different until the very last moment, when the hydrogen cells filling the balloon ignited one by one, causing explosive damage as the fuel tanks erupted. Remarkably, just under 2/3 of the passengers and crew survived, thanks only to its proximity to the ground and the extended duration of the disaster. Most victims, however, were severely burnt, and grief ripped through the families of the 35 lost souls. Airships had been a regular sight across city skies, carrying army personnel, passengers, and freight across and between continents. Most airships utilized hydrogen as a way of filling the balloon, as its buoyancy is well above that of air. But hydrogen also boasts another property. It is extremely flammable. Most evidence points to the cause of the Hindenburg disaster as a hydrogen leak in the fuel tanks. When this hydrogen mixed with oxygen in the air, the gas holding up the balloon became ready to blow, and it is thought that a simple flash of static electricity provided the source of ignition, thus ending the era of airships with almost immediate effect. Hydrogen. One proton, one electron. Simplicity itself. This most basic atomic structure is odorless and tasteless, and it will combust when exposed to even the lowest concentrations of air and in ignition. But even that fatal destruction is far from the full power held within this small orbital system. Nagasaki, Hiroshima. These cities act as reminders of the horror that humankind can unleash upon itself just by splitting the atom. Fission. But fusion-based hydrogen bombs are far more devastating. They are up to 1,000 times more powerful and could easily kill the populations of entire cities in an instant. And many of the scientists that worked on creating these nuclear bombs were also physicists and astronomers themselves, looking to the fusion of hydrogen within stars for inspiration. But at around the same time, hydrogen became the focus of another group of astronomers, for a slightly less bombastic, but no less remarkable reason. Jon Oort had risen to the top of the astronomical world by questioning the assumption that the Sun was at the center of the Milky Way. He had shown that the Sun was in fact 30,000 light-years out, in a galaxy that was rotating just as a spiral would. Now, however, he was half in hiding, having protested and resigned over the dismissal of his Jewish colleagues. The war was raging, and Holland was under German control. Research and the exchange of knowledge was fraught with risk. But the pull of academia was too strong to keep him solely in his country retreat. For Oort was still in pursuit of a perfect model of our galaxy. But to do so, he had to overcome a challenge. For our Milky Way is shrouded in dust. He would need to pierce through the obscuring interstellar clouds and see further than optical telescopes would currently allow. But how? The answer finally came in a smuggled issue of an astrophysical journal, which spoke of the promise of detecting radio waves from the Milky Way. Radio waves have long wavelengths and are immune to the obscuring dust. In addition, the interstellar gas feeding whole stellar nurseries might emit radio waves, illuminating the galaxy on much grander scales than individual stars. Oort realized that with a subtle radiospectral line, he could map our galaxy far beyond the boundaries of optical light. And so in 1944, Oort tasked student Hendrik Christopher van der Helst with searching for a way to determine the shape of the Milky Way by detecting and mapping the invisible hydrogen gas that pervaded it.
Dang, it's pretty.
There are many ways in which an atom can emit light. Tiny transitions of electrons between two energy levels in an atom cause the emission of photons with an equivalent energy, or wavelength. Different processes lead to different wavelengths. Oort and van der Helst needed a transition that was common enough to occur regularly across the sky, and that produced an intensity such that astronomers could clearly measure its spectral line. Having worked meticulously through the atomic transition probabilities, he found a promising candidate. Within the first energy level of the hydrogen atom was a hyperfine structure, a splitting of the energy level into sublevels, populated according to the electron's values of the atomic property spin. If an electron holds the same spin value as the proton it orbits, it occupies a higher energy level. If opposite, lower. Sometimes electrons in the higher energy level spontaneously change spin, in a rare occurrence called a spin-flip transition. The electron moves to the lower energy level, emitting a photon of energy precisely equal to the hyperfine energy gap. This photon has a frequency of 1420 MHz, or a wavelength of 21 centimeters, placing it within the low-frequency domain of the electromagnetic spectrum. Perfect for a radio telescope. Van der Helst presented the 21-centimeter emission line as the key to mapping hydrogen across the Milky Way, a special second sight that would reveal structure far beyond what the stars could tell us. But was the probability of success too low? The probability of an electron spontaneously flipping in spin was minuscule, and so to have such a rare event be detectable, the volume of hydrogen would need to be huge. We can imagine this like trying to find that elusive rare trading card in your trading card collection. If your card makes up 100th of those manufactured overall, you will be lucky to find it in a single pack. By several hundred packs, though, and the rare becomes observable, the Charizard commonplace. In the mid-20th century, astronomers could not be sure at all of the amount of hydrogen in space, but there was general skepticism that it could be so much as to make the 21-centimeter spin-flip transition observable. Oort salvaged 2 leftover German antennas and set to work. However, though he was a well-respected and expert astronomer, the electrical engineering knowledge required to construct an interstellar listening device was a unique skill, and one that he entirely lacked. And, unbeknownst to them, at the same time, a group of physicists in the US had also taken interest in Van der Helst's theory, but with the expertise to follow up. Edward Purcell's head had been turned because of his background in subatomic matter, and his PhD student, Harold Doc Ewan, had a background in radar physics. They too set to work immediately. Ewan used plywood and copper plating, expertly installing the electronics to construct a pyramidal horn radio antenna. These odd-shaped devices, like an ice cream cone on its side, were less susceptible to human-made interference from radios and other electric equipment. The horn was installed hanging out of the 4th-floor window of the lab on campus, the naive scientists not foreseeing the risk that students would enjoy using the horn as a target for snowballs. The device didn't need to be big or steerable, because they would not be scanning across the skies in their search. Whether diffuse or dense, the hydrogen should be everywhere. And so, on Easter morning, March 1951, they successfully detected the 21-centimeter galactic emission line. It had worked. Van der Helst was right. Fortunately, a quick two-way sharing of knowledge began, with the Americans teaching the Dutch how to construct the experiment, and the Dutch explaining to the Americans the astronomical context of what they had achieved. This generous sharing of knowledge meant that, within the space of 3 months, the global radio astronomy community was primed to map our galaxy's hidden corners and far-off lands. By searching for such a specific spectral line, astronomers could now not only identify where the gas lay in the galaxy, but also whether it was moving towards or away from us by measuring the redshift of the light. And it is in this way that radio astronomers first showed beyond doubt that the Milky Way was both a spiral in structure and that it was rotating. Today, we still search for this line using ever more advanced telescopes, reaching further and further and discovering new arms and branches to our home galaxy. But what does this mean for the cosmic dark ages? Radio telescopes give us the means to light up the invisible gas that permeates galaxies. Hydrogen is the most simple of elements and the main constituent of normal matter in the universe. Before planets, before stars, and before galaxies, there was just this gas, flowing through the universe and becoming trapped in the vast web that dark matter had woven. This gas was still there when darkness fell, invisible to the optical onlooker. But look again with eyes tuned to a wavelength far removed from the rainbow. Look instead with eyes tuned for 21 centimeter radiation, and the universe becomes bright with structure, even during the darkest times. The surrounding hydrogen gas follows where the dark matter went before it, collapsing onto the filaments and halos. Simulations show the hydrogen tracing the dark matter structure almost perfectly under the cover of darkness. And so, we have found the means to trace the earliest stages of star and galaxy formation, a single wavelength of light, 21 centimeter radiation. The universe was dark to our eyes for hundreds of millions of years as the ingredients for star formation gathered and ignited. But with other eyes tuned to longer wavelengths, we would have been able to see these nascent environments and know where the first stars would form. But do the first stars really mark the end of these dark ages? Would darkness really lift with the flick of a switch? Our seas and oceans are the largest habitat on Earth, and one of the most varied. As we snorkel in their crystal clear waters, schools of brightly colored fish captivate us. Sinking below the surface, however, our eyes steadily become useless as the sunlight dwindles. By 10 meters down, the reds, oranges, and yellows have been absorbed, and you struggle to see with only 70% of the surface light. By 50 meters down, the greens and violets have been excised from the rainbow too. And yet still, the ocean descends, and still, life is all around you. The fish even become redder as you fall, evolution having noted that in an environment lacking red wavelengths, they will appear almost invisible. 200 meters marks the twilight zone, a dim, monochrome world. You begin to see the glow of bioluminescent animals, such as the hatchetfish, float past, creating their own light to match the waters above so that they don't get seen and snapped up by predators below. At 300 meters, you are enveloped in darkness, working with only the light of a moonlit world on the surface. A giant squid glides serenely past you, all 10 meters of it, its football-sized eyes scanning you for threat. At 850 meters, your eyes can no longer gather enough paltry photons to activate the optic nerve. The midnight zone begins, and in some places may even continue for several more kilometers. On Earth, then, life has adjusted to total darkness and learned to live despite it, hidden from the only way our eyes know how to look. And so, during the dark ages of the universe, we know too that the black was not empty. There was structure in place behind the scenes, a dark matter web that drew in nearby hydrogen and built the foundations of the universe, brick by brick. And all over the universe, by about 200 million years after the Big Bang, gravity would crush these dense pockets of hydrogen just enough to ignite the engines of stars. In every direction, the lights blinked on, slowly illuminating the Dark Ages. But was the oblivion that preceded this visible illumination really so empty of light? It may have been dark in the optical, but was it truly dark in other wavelengths, too?
Alas, the ship rides through the morning. You know it's calling, me back home. Put down the sorrow and dance to me.
Despite emitting across all the wavelengths of the electromagnetic spectrum, the first stars found their nascent cries muffled by the murk of a deep ocean of hydrogen. The path was not entirely clear for this new light. While gravity had swept some hydrogen up to make the first stars themselves, there was more than enough remaining to swaddle the newborns. As the first engines of fusion started up and the resulting photons found their way out from the core to the surface of the star, they encountered clouds of atoms, ready to absorb them before they could make it much further. An observer of these first stars would likely notice little wrong with the light, as hydrogen absorbs only 4 visible wavelengths. The rainbow of its visible spectra would therefore be complete, except for discrete emissions within the red, cyan, blue, and violets. At the lower wavelengths into the UV, the first stars emitted strongly, but a removed observer, whether a human equipped with a telescope or an insectoid with UV-sensitive eyes, would have seen a dimmer star. But before too long, these first stars began to change their surroundings, and in a surprising way. Our traditional view of an atom has been passed down to us from the early 20th century physicist Niels Bohr, a compact nucleus of protons and neutrons orbited by satellite particles, called electrons. But that is not how many of the atoms in our universe pass their time. Almost 99.9% of the matter in the universe is in the form of a plasma, a mix of separated electrons and ions. The highest energy level in a hydrogen atom is 13.6 electrovolts. If the atom absorbs a photon carrying more than this amount, the electron is energized to such a degree that it overcomes the bond with its proton and becomes an autonomous, free particle. The hydrogen atom is said to be ionized. In the immediate aftermath of the Big Bang, the high temperatures and frequent collisions rendered all normal matter ionized, before it cooled and came together as full hydrogen and helium atoms with their requisite electrons at the beginning of the Dark Ages. But not for long, for quickly following the end of the Dark Ages is a new stage in the history of the universe, the era of re-ionization. The first photons from a first star and later a first galaxy ionize their immediate surroundings, creating a shell of ionized hydrogen through which the next photons can get a little farther before they meet an intact hydrogen atom. Over time, these bubbles of ionized hydrogen get larger and larger, connecting and merging such that the hydrogen gas that we observe around us today is almost all ionized. It is still a mystery exactly how the universe got to be in the completely ionized state that we observe it in today. The first stars could not produce enough ionizing photons in their short lifetime to fully clear the way. Instead, it seems more likely that, while the first stars began the process, it was the first galaxies that finished the job. Full of the many and long-lived second-generation stars and a central black hole accretion disk spewing radiation, they could easily ionize the universe before the first billion years of time had passed. Then, 1 billion years after the Big Bang, in a universe full of ionized gas, light could travel with the same freedom it can today. The epoch of re-ionization was complete, and with it, the Dark Ages was truly over. Together with the Dark Ages, the epoch of re-ionization is an almost totally missing era in the timeline of our universe's evolution. There have been a handful of galaxies observed within the latter epoch, but not enough to make anything but the most tentative scientific conclusions about the state of the universe over the whole era of the first stars. Doing so would be like making conclusions about the entirety of human history based on a single bone from each of 5 random centuries. And so when the James Webb Space Telescope launched on December the 25th, 2021, expectations were high that we would see many more galaxies from within that lost time. For Webb is infrared, allowing it to probe even further back in space and time than Hubble. When we peer at the Hubble Deep Field, we can see a range of galaxies from many epochs, the oldest visibly reddened because of the expansion of the universe, redshift. But while galaxies emit across the electromagnetic spectrum, as we observe the spectrum of light from older and older parts of the universe, there will be a point at which most of the light has redshifted out of the shorter wavelength domain. Hubble cannot produce images of galaxies whose spectra have redshifted out of the visible wavelengths. Webb, however, an infrared instrument, can see light from further into the past, because it can still detect the photons even though they have redshifted out of the visible wavelengths and into the infrared. Able to look deeper and farther than Hubble, Webb has already observed some of the earliest galaxies we have ever seen in the universe, barely 350 million years after the Big Bang. But even this Goliath of astronomy has a limit. While Webb has provided a fascinating insight into early galaxy formation, to reach further back, to reach the mysterious Dark Ages, we need a different instrument entirely. Hubble, an optical telescope, and James Webb, an infrared telescope, ultimately provided tiny samples of the sky, both in image space and across time. To push further to the earliest moments of the epoch of reionization and the Dark Ages requires the longest wavelengths we have: radio. As we look further back in time, we observe more of the universe per pixel. Thus, while we may be able to see the Sun and galaxies such as Andromeda and the Whirlpool in exquisite detail, as we move to the earliest times, the resolution achievable is simply so low that we cannot see individual stars or even individual galaxies. We need something on a much larger scale, and radio loud. And this is where Van der Helst's Hydrogen-21 line comes into its own. As we have seen, in the early universe, clouds of hydrogen pervaded the cosmos, and these can provide a means for us to observe the progression of the epoch of reionization, the 21-centimeter line. We can observe the Dark Ages as a cacophony at the redshifted 21-centimeter wavelength. Then, as the ionized bubbles grow and merge, we can trace them in the absence of 21-centimeter radiation, like a cosmic Swiss cheese. The shape and speed they grow can tell us much about the sources that are producing the radiation: population 3 stars, baby black holes, and even the earliest forms of galaxy. Radio telescopes hold the key to lighting up the Dark Ages, but the experiment itself is one of the hardest in astronomy. The signal is incredibly small, buried under the photons of our bright galaxy that cannot help but fall on the same antennas. And so, is it even possible to find this signal of reionization and illuminate the Dark Ages? Imagine yourself deep in the Australian outback, in a desert landscape void of human life, the red dust broken only by rocks and desiccated shrubs. The powerful heat of the day shimmers in the dry air, no hint of recent or forthcoming rain. But as you walk, you see evidence of life. Sheep and cattle grazing on a land that humans largely find too hostile to occupy. And these animals don't just experience this land differently, they see it in an altogether different light. The lenses and sensors embedded in our retinas can result in vastly different views and understanding of the same environment. Humans are usually born with color-sensitive cones tuned to red, green, and blue. But the cows and sheep you pass cannot see the shades of red land at all. The snake that slithers past your feet also lacks the ability to see shades of red. But it has an ability you do not, the ability to sense infrared. Here you find another companion as a scorpion scuttles in front of you. This scorpion can detect UV light too, and even has the rare quality of fluorescing when exposed to these wavelengths. The animal kingdom is alive with examples of adaptations to different levels and wavelengths of light. Indeed, humans are rare for only seeing in the optical. Instead, we have emulated the animal kingdom by creating technology to help us perceive our environment in the UV, infrared, and X-ray wavelengths. We have also invented entirely new methods, not shared by any other being on Earth, to access the longest wavelengths, the radio waves. In the pursuit of long-distance communication, we built our own interface with the radio universe, learning through trial and error how to listen in to a signal from a different room, a different country, a different continent, and then, quite by accident, we picked up the signals of the stars and planets and meteors, and radio astronomy was born. We had developed the means to communicate to the distant universe and into the distant past. Only humans can communicate at these longest wavelengths, having carefully created for themselves a new kind of eye. As you walk on through the outback, you come across a strange sight. Standing on the dirt lie strange metal sculptures. Some are bow-tie shaped, some look like reflective tables, and others look a little like trees, their spikes evoking cacti. But these bizarre metal structures in the Australian outback are not discarded abstract art. They are an interface to a universe that only we have access to. They were a gate to the past, to a time when the stars were only just forming in the densest nodes of that dark matter web. Humanity has also woven a web, creating societies and cities that spread out across the Earth. This spread, however, is not even. Civilization built up around rivers and seas, driven by a need to trade. Over time, the harsher terrains, like the outback, were abandoned for the promise of amenities and safety in numbers. And for radio astronomers aiming to detect the weakest signals from space, the emptiest voids on Earth are an ideal location to set up their experiments. Deep in the Australian outback, covering an area of 49,500 square kilometres, the Murchison Shire hosts a population of just 100 people. Here, in one of the quietest places in the world, away from human technology and interference, radio astronomers have spent over a decade searching for signs of the Dark Ages. And in 2018, one of these telescopes received a signal that was very strange indeed. This telescope is humble, simple even, and far from the standard image that we associate with astronomy. For EDGES is a radio telescope. Short for Experiment to Detect the Global Era of Reionization signature, EDGES works like a TV or radio antenna, receiving radio waves and converting them into a digital signal. It is a sensor tuned to that cosmological 21-centimeter line emitted from the era of reionization and the first stars. These photons have been traveling to us from 13.7 billion years ago, redshifting such that we detect them at wavelengths stretched from 21 centimeters to about 2 meters. By building a telescope to this scale, those wavelengths create a voltage across the telescope, producing a digital signal that we can examine for its provenance and its intensity. EDGES, in effect, measures the temperature of the hydrogen across the Dark Ages, retuning and reobserving at different wavelengths to scan photons from across hundreds of millions of years. Though in the beginning the gas is cool, coalescing around the dark matter web, when the first stars form and begin emitting radiation of their own, they heat their surroundings, imprinting a change in the 21-centimeter signal. Never moving, never making a sound, its human operators thousands of miles away, EDGES listened patiently. By observing at different wavelengths, the telescope could probe further and further back through the Dark Ages, looking for any sign of the first stars forming. The data was untidy. The imprint of the electronics of the telescope and radiation from all around our local galaxy had to be modeled and removed carefully to see if there was a quiet whisper underneath. The team of astronomers found they could recover a signal below all the noise, a change in temperature at approximately 180 million years after the Big Bang, potentially the first direct observation of the era of the first stars. A birth certificate. This discovery alone was momentous enough to revolutionize a field starved of data. But there was more. The temperature of the gas was all wrong. The data suggested that the gas in the universe during the Dark Ages was far colder than any model had predicted. Every model of our universe developed over decades that fit all other observations was suddenly useless. Astronomers were shocked, and there was years of speculation as to the cause of this unexpected cooling. Perhaps there had been errors introduced in the data during the cleaning of the radiation picked up from the galaxy. Perhaps this coolness was an illusion, and there was a mysterious background of radiation that was leading to the gas seeming cooler. Or perhaps, and most sensationally, dark matter could interact with the gas in early times, cooling it down through collisions. The claim was that in a cooler universe, dark matter behaved differently. This was an extraordinary idea, and astronomers met it with healthy skepticism. The need for more evidence spurred the conception and production of a fleet of new telescopes around the world, all aiming to validate the EDGE's result. However, with time, there was more and more focus on the first and most mundane explanation. The analysis was simply incomplete. The mysterious signal was noise that had not been correctly removed. The EDGE's team had carried out their due diligence, checking all they could, but it was only with wider community help that they could try alternative observation and analysis methods that could reproduce their own result. Saras, an antenna floating on an Indian lake, was the first experiment to confirm with sufficient confidence that the EDGE's result was not to be trusted. They couldn't find such an extreme signal. And so the old models were retrieved from the rubbish bin, and calm was restored. But what about the birth date of the first stars? Is it 180 million years after the Big Bang? Can we trust EDGE's enough on this at least, if not the exotic nature of dark matter? The search is far from over. The Dark Ages signal is hundreds to thousands of times smaller than the radiation from our own galaxy, and the experiment is one of the toughest in astronomy. EDGE's and Saras have begun that search, testing methods and new technology, exposing problems in our theories. Indeed, in that same outback, the Murchison Wide Field Array has been listening for the bubbles of the epoch of reionization using bow tie antennas, called the ear that listens to the sky by the local indigenous people who have granted the use of their land. Soon, both are to be joined by the most ambitious radio astronomy observatory ever built. The square kilometer array is to comprise 130,000 antennas spread across the Murchison Desert. This telescope is so sensitive that it could hear an airport radar signal on a planet 10 light-years away. And it can look back across the first billion years of our universe into the epoch of reionization and the Dark Ages. Despite being one of the quietest places on Earth, the sound of humanity and the interference of the atmosphere is still too great for us to look back into the oldest stages of the Dark Ages. While we continue gathering data, improving our models and methods, we must also look to the next step. We look for quieter places, such as the moon. Indeed, testing has already begun to aid the sending of antennas to the far side, using the moon itself as a shield against the onslaught of mobile phone, radio, and satellite signals. And so the universe was dark for almost 200 million years, but really only to our eyes. To the metal antennas in the desert, our interface with the stars, there was never darkness, just a time of quiet industry. The gas and dark matter worked together to form stellar nurseries, and in the longer wavelengths, the universe was bright with 21-centimeter photons throughout. But it was the light bursting forth from the first stars that changed the universe to that we now perceive. Those stars would in turn come together to form galaxies, long-lived and bright. The cosmic dark ages would eventually meet their end. You've been listening to the entire history of the universe. Subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.
Introducing the Ferrero Rocher Chocolate Bar. Crunchy hazelnuts, smooth chocolate, creamy filling. Make any moment worth celebrating. Ferrero Rocher.
Dyson's new digital motor gives you 262 air watts of suction and a detangling cleaner head in the most powerful cordless vacuum. And it adapts to clean everywhere. Now in Prussian blue and rich copper. Only at Dyson.
Until Voyager arrived in the Neptunian system, this was the least understood of all the planets. Invisible to the naked eye, Neptune was a world hidden from view. Even through the most powerful of telescopes, it appeared as no more than a blurry ball of blue and green. The fourth largest planet in the solar system by volume, and the third largest by mass. From afar, we knew nothing of its atmosphere or its structure, and had only faintly observed two of the moons in its orbit, Triton and Nereid. This was a planet that had remained very firmly in the darkness, a distant world that had clung on tightly to its secrets for over 140 years. Even the discovery of Neptune played out in the darkness. The last of the planets to be discovered, it is the only one whose existence we predicted before it was ever observed by the human eye. For centuries we stared at it without knowing what we were looking at. Almost certainly, Galileo was the first human to peer at Neptune directly, during a series of observations at the end of 1612 and the beginning of 1613. The data he plotted with his newly invented telescope led him to believe this was a fixed star in the night sky, not a planet. Over the next 200 years, many astronomers must have fixed their gaze on this dim star without realizing the significance of its bluish light. But the first hint of its true nature would appear not in an eyepiece, but in a set of astronomical tables. In 1821, the French astronomer Alexis Bouvard published Tables Astronomiques, a set of tables predicting the orbits of the three outer planets, Jupiter, Saturn, and Uranus, based on Newton's laws of motion and universal gravitation. Over the next few years, Bouvard's theoretical work would be tested against the movements in the night sky, and his painstaking calculations were rewarded with the confirmation that actual observations of the movements of Jupiter and Saturn adhered precisely to his mathematical predictions. However, Uranus refused to behave quite so compliantly. The movement of the then farthest planet deviated substantially from Bouvard's predicted path, and this led him to make a wild suggestion. Either Newton was wrong, or perhaps there was an as-yet undiscovered planet lurking in the darkness, distorting the passage of Uranus through its gravitational interaction. A flurry of astronomers sped to find the hidden planet, the ultimate prize for any stargazer, as an acrimonious race kicked off between the British and French to predict the planet's location. On the British side of the Channel, the Cornish astronomer and mathematician John Couch Adams became obsessed with Bouvard's hypothesis and was convinced he could use nothing more than pen and paper to determine the size, position, and orbit of this hidden world. By September 1845, Adams had at least partially completed his calculations, but unknown to him, almost simultaneously, the French mathematician Urbain Le Verrier in Paris was completing his own complex computations of Uranus's path and the elusive eighth planet. By the summer of 1846, Le Verrier had played his hand and announced to the Académie des Sciences on the 31st of August that he had calculated a predicted location for the missing planet. Revealing his work just 2 days before, Adams secretly sent his own prediction in a letter to the Royal Greenwich Observatory for verification. In what must be one of the most close-run races in scientific history, Leverrier engaged the Berlin Observatory in the search for his planet. And at 00:15 on the night of the 24th of September 1846, Johann Galle, with the help of his assistant Heinrich Darré, looked through his refracting telescope and became the first person to knowingly gaze at the eighth and furthest planet in the solar system.
What makes Thanksgiving special? For Ilka, it's making her family and friends feel welcome.
They call me the grandma of the world. If you were over and playing with us, you were part of our family and you were going to eat.
Food brings Ilka and her loved ones together. With the support of her local pantry, there's enough to go around. This holiday season, join the movement to end hunger. Get involved at feedingamerica.org/themovement.
We work in the dark to serve the light. Yeah, I'm in pajama. Yeah, I'm chasing karma. See some people, people can't. You have become one of us. Is it just a mirage?
A planet that had taken decades to locate was found in less than an hour, and within 1 degree of the position Leverrier had calculated. Even today, the exact credit for the discovery of Neptune is still disputed, but in the winner-takes-all world of astronomical discovery, it's Leverrier whom history records as the discoverer of Neptune, the man who discovered a planet with the point of his pen. It took another 143 years before we would visit Leverrier's planet and witness a dynamic, violent, and volatile world. As Voyager drew closer, it began to return a precious set of images that remain to date our only close-range record of this planetary system. At first flying past Nereid, the third largest of Neptune's moons, Voyager captured our only image of this distant world traveling on its massively eccentric orbit around the planet. But it was the images of Neptune itself that became increasingly astounding. Painted across the surface of the planet, Voyager revealed banks of methane clouds that were being whipped around by high-altitude winds at speeds of over 2,000 kilometers per hour. At least 5 times stronger than the most powerful winds ever measured on Earth. These were the highest wind speeds we'd witnessed anywhere in the solar system. It wasn't just violent winds that we saw through Voyager's eyes. Great hurricane-like storms could be seen moving across its surface, the largest being an Earth-sized storm system similar to the Great Red Spot on Jupiter, which became known as the Great Dark Spot. Voyager took multiple images of this vast storm system as it sped past the planet, skimming the cloud tops of the northern pole from a distance of just 4,400 kilometers as it reached its nearest approach on the 25th of August, 1989. No one had expected such massive storms to be brewing so far from the sun. But just 5 years later, with the Hubble telescope up and running, we peered back towards Neptune and found that the Great Dark Spot had disappeared. Unlike the giant storms on Jupiter, which we've witnessed playing out for centuries, it seems that the weather on Neptune is far more transient, with the largest events coming and going within the space of a few years. The intense weather systems that we witnessed on Neptune remain a tantalizing puzzle. The planet is on average 50% further from the Sun than Uranus, and receives just 40% of the sunlight that hits its sister world, and the surface temperatures of both planets are equally intensely cold. In fact, the temperature of Neptune's outer atmosphere is one of the coldest places in the solar system, with temperatures at its cloud tops measuring around minus 220 degrees Celsius. Orbiting this far out in the far frozen reaches of the solar system explains the blandness of Uranus's weather. But why would Neptune, even further from the Sun, be so active? The answer, we think, lies in a mysterious and powerful source of heat that we have detected coming from deep within the planet. All of the planets, including Uranus and Neptune, have some residual heat locked deep inside them. And much of this is the thermal energy that remains from the endless collisions of their creation. as well as the heat released by the radioactive decay of certain elements in the core. However, this far out, Uranus has rapidly lost this heat, and today radiates just 1.1 times the energy it receives from the Sun, so that the heat radiating from its core is too little to drive any kind of dynamic weather system through its atmosphere. Neptune, it seems, has a far warmer heart, and Voyager was able to reveal that the most distant planet radiates 2.61 times as much energy as it receives from the Sun. It's these unexpectedly high temperatures that help to explain the violent storms we see in its atmosphere. As the heat makes its way from the core of the planet and out into space, it churns up the entire atmosphere, creating winds of extreme ferocity, and once they start, there is little to stop them. Neptune, like Uranus, is an ice giant, a planet composed of a rocky core and a mantle made up of water, ammonia, and methane ices, surrounded by a cold gaseous atmosphere. With no solid surface on the planet, there are no mountains or continents to break up the flow of the atmospheric gases, so this means the winds can whip around the planet, picking up speed until they are quite literally supersonic. All of this helps to give us a reason for Neptune's extreme weather, but not an explanation. Voyager 2 was unable to reveal why Neptune and Uranus are so different, and we still don't know what it is about these planets' formation that left Neptune with far more residual heat, making it the far more active of the two. Neptune's active atmosphere was not the only surprise Voyager returned to us with the pictures from its two-camera system. In vibrant and vivid detail, the images also revealed the solar system to be home to not one, but two blue planets. Neptune is a bright blue world, but with no liquid water on its surface, we know that the origin of this color cannot be the same as here on Earth. This deep cobalt color must be produced by something else in Neptune's atmosphere, and Voyager provided the answer. Using its onboard spectrometer, Voyager was able to measure for the first time the composition of Neptune's atmosphere, and found it to be comprised of 80% hydrogen, 18.5% helium, and 1.5% methane. Methane was by far the smallest component, yet this is the key to understanding Neptune's blue hue. The light of the sun contains all the colors of the rainbow, but as it hits the surface of a planet, it interacts in different ways depending on the molecules it encounters. In the case of the Earth, the water that covers our planet absorbs all of the red light in sunlight, so as the sun strikes the surface, only the blue is reflected back. It's the same with all the plants on our planet. The chlorophyll absorbs the blue and red light, so that only green is reflected back. On Neptune, there is no water to turn the planet blue. Instead, it's the methane that absorbs the red light of the dim and distant sun, reflecting the blue light back out into the darkness. But things aren't quite as simple as they first appear. Uranus is also a blue world, but just that bit paler and greener in shade compared with its more distant sibling. And yet Uranus also has methane in its atmosphere. In fact, it has slightly more. So Uranus, not Neptune, should be the darker shade of blue. Why is this? Well, quite wonderfully, we still don't know. Voyager looked for other constituents in Neptune's atmosphere that could account for the deeper blue, but it found nothing that could explain the discrepancy. So for now, the many differences between these two worlds remain a mystery.
Known as a passionate artist, known for loving the outdoors, known for getting everyone together. No one wants to be known for cancer, but a treatment can be. Keytruda is known to treat cancer, FDA approved for 16 types of cancer, including certain early-stage cancers. One of those cancers is triple-negative breast cancer. Keytruda may be used with chemotherapy medicines as treatment before surgery, and then continued alone after surgery when you have early-stage breast cancer and are at high risk of it coming back.
Keytruda can cause your immune system to attack healthy parts of your body during or after treatment. This may be severe and lead to death. See your doctor right away if you have cough, shortness of breath, chest pain, diarrhea, severe stomach pain, severe nausea or vomiting, headache, light sensitivity, eye problems, irregular heartbeat, extreme tiredness, constipation, dizziness or fainting, changes in appetite, thirst or urine, confusion, memory problems, muscle pain or weakness, fever, rash, itching or flushing. There may be other side effects. Tell your doctor about all your medication, immune system problems. If you've had or plan to have an organ or cell transplant, receive chest radiation, or have a nervous system problem.
Keytruda is an immunotherapy and is also being studied in hundreds of clinical trials exploring ways to treat even more types of cancer. It's true. Keytruda from Merck. See all the types of cancer Keytruda is known for at Keytruda.com and ask your doctor if Keytruda could be right for you.
After over 12 years of traveling, Voyager 2 completed its grand tour of the solar system. A tiny explorer that had set out from Earth and traveled across 7 billion kilometers of space on a single extraordinary journey to explore all of the outer worlds of the solar system: Jupiter, Saturn, Uranus, and Neptune. But before it began its long, lonely journey into the darkness of interstellar space, there was one more brief rendezvous left on its itinerary. While in the Neptunian system, Voyager had made endless discoveries, including the detection of a faint ring system and the confirmation of 6 new moons in orbit. But in those final hours of close contact, as it flew across the north pole of the planet, the mission scientists back at JPL had instructed the craft to make one last intrepid maneuver: a close flyby of Neptune's giant moon, Triton. Just 5 hours after nearly touching the cloud tops of Neptune, Voyager traveled within 40,000 kilometers of the Neptunian moon and returned the first pictures of this strange and distant world. The British astronomer William Lassell first spotted Triton on the 10th of October 1846, just 17 days after the discovery of Neptune. As astronomers clamored to observe the newly identified planet, it was Lassell with his homemade telescope who noticed the satellite first. Although not officially named until many years later, Triton would remain the only known satellite of Neptune for over 100 years, until the discovery of Nereid by Gerard Kuiper, more of him later, in 1949. As Voyager returned the first images of this distant moon, it immediately became apparent that just like Neptune, Triton was far more active than we had ever imagined. Here in the furthest reaches of space, the 7th largest moon in the solar system was far from a frozen, inactive rock. It was a geologically active world, with features unlike anything we had imagined. Able to image just 40% of its surface due to the fact that most of the northern hemisphere was in darkness, Voyager revealed Triton to have a sparsely cratered exterior, with a strange network of ridges and valleys covering its entire surface, including in the western hemisphere, a region dubbed the Cantaloupe terrain because of its striking similarity to the skin of a melon. All of this evidence pointed to the fact that the surface of Triton was young, not battered and ancient like that of our moon. A surface that, even though it had been recorded by Voyager's instruments as one of the coldest places in the solar system at minus 235 degrees Celsius, seemed to be being resurfaced by active volcanism occurring across the planet. But this was not volcanism as we understand it here on Earth. There is no molten rock beneath the surface of Triton. This is an ice world, with the surface covered in a frozen mixture of nitrogen, water ice, and carbon dioxide. Any volcano that exists here would be a cryovolcano, erupting water, ammonia, and methane from below the surface. Cryomagma that would immediately solidify in the extreme low temperatures at the surface. And as Voyager peered closer at the surface of Triton, it captured a series of images of the southern polar region that appeared to provide evidence of such geological activity. Lurking amongst the flat volcanic plains and rift valleys was a set of distinct features that at once caught the eye. Scattered across the surface were what appeared to be at least 50 dark plumes. Voyager was traveling so fast and so far away from the moon that it was unable to get close-ups of these intriguing plumes, but we are certain that they are the evidence of ice geysers, and that the dark streaks are dust deposits left on the surface by the eruption of these geysers. According to planetary scientist Noah Hammond, it was a big surprise to see active geysers going on Triton, shooting 8 kilometers into the air. And we think these geysers might be forming as a result of nitrogen ice, which is being vaporized by the sun. Both of the geysers that Voyager 2 observed, which are currently blowing up, are concentrated on the warmest part of Triton, where the sunlight is striking the hardest. And as the sunlight pierces through the nitrogen ice, it starts to turn that nitrogen ice back into a gas again, and that gas builds up and builds up until it has enough energy to break through the ice and lift dust all the way up into the atmosphere. Further analysis of the images suggested that at least 4 of these geysers were active at the time of Voyager's flypast, belching clouds of ice and dust 8 kilometers up into the thin Neptunian atmosphere before falling back down to the surface over 100 kilometers downwind. Perhaps even more astonishingly, we have been able to actually formulate a hypothesis for the mechanism that lies beneath them. The key to understanding why this wondrous geological activity occurs in the most unlikely of places seems to involve their location on the surface of Triton. From the imaging data that Voyager 2 returned, it seems the geysers tend to erupt on the most sunlit part of Triton's surface. From a distance of 4.5 billion kilometers, the sun's rays are faint, and the amount of thermal energy landing on the surface is low. But combined with the specific chemistry on Triton's surface, the effect of the sun can still be dramatic. What seems to be happening is that sunlight falling on the thin layer of nitrogen ice that covers Triton is penetrating the surface and heating up a layer of darker methane particles a meter below the surface. The methane acts as a subsurface greenhouse gas, trapping the heat below the surface and radiating that heat back up through the frozen nitrogen. Even though this mechanism creates a temperature difference of just 4 degrees Celsius between the ambient surface temperature and that of the warmer interior, this difference is enough to melt the frozen nitrogen and create pockets of gas. Sitting beneath the nitrogen ice, that gas is kept under pressure, building up until ultimately it punches through the nitrogen ice, creating the geysers of Triton and carrying the dark ice particles up to 8 kilometers into the sky. Although the faint light of the sun is just strong enough to power Triton's geysers, it's simply too weak to have driven the other geological processes that have created the network of valleys and crevasses we see all across the surface. It seems that something in Triton's past must have heated the moon enough to drastically alter its terrain. And a potential clue to the source of that ancient heat can be found in the oddity of Triton's orbit. Unlike every other large moon in the solar system, Triton orbits in the opposite direction to the spin of the planet. Traveling around Neptune in its tidally locked orbit, with the same side facing inwards at all times, Triton orbits in a clockwise direction, while Neptune spins on its axis every 16.11 hours, anti-clockwise. Such dissonance between planet and satellite suggests that it is very unlikely that Triton and Neptune formed at the same time. A planet and moon system fashioned from an identical collapsing cloud of gas and dust at the same moment would tend to spin and orbit in the same direction as the spin of the initial dust cloud, just like the overwhelming majority of moons we see in the solar system today. So the most likely explanation is that Triton joined Neptune much later, a visitor to the Neptunian system that, unlike Voyager, never left. Like Uranus, we don't know for certain the deep history of Triton, but all the evidence from its orbit and surface features point to the possibility that long ago Triton was not a moon at all. To understand where it might have come from, we need to look beyond the Neptunian system and peer further out into the darkness.
Sawdust settles and the engine finally roars. The thing you care about most is a job well done. But when you get your tools from Harbor Freight, something about the job feels a little different. Your wallet. Because we believe no matter what you're working on, you need high-quality tools at a great price. And that's what we have in stock here. So whatever you do it for less at Harbor Freight. Quality tools, lowest prices.
It was only relatively recently that we confirmed the existence of a region of the solar system now known as the Kuiper Belt. a disk of millions of objects that stretches out from the orbit of Neptune to at least 50 AU from the Sun. Similar to the asteroid belt in structure, but far larger in scale. We had long speculated that such a region might exist, but it wasn't until the discovery of an icy object known as 15760 Albion in 1992 that we were able to put together a body of proof. The discovery of this region was a turning point in our knowledge about our solar system. According to Alan Stern of the New Horizons mission, the Kuiper Belt was so revolutionary because, as it's so far from the Sun, the temperatures out there are almost absolute zeros, so everything is so well preserved. It's an archaeological dig, if you will, into the early history of our solar system. So it's a scientific wonderland, and you put all that together, redrawing the map and putting us in our place about who's the oddball now. It's not Pluto, it's the Earth or Jupiter that's the oddball. And then having this museum piece placed in the solar system where everything is so well preserved. I can't think of a bigger discovery that we've made that's reshaped our thinking so profoundly in all the decades of space exploration. Albion was the first trans-Neptunian object to be identified since the discovery of Pluto and its moon Charon. And this finding launched a flurry of further revelations that now put the number of identified objects in the Kuiper Belt region at around 2,400. We think there are at least 100,000 objects bigger than 100 kilometers wide in the Kuiper Belt. Just like the asteroid belt, this dispersed region of debris is composed from the remnants of our solar system's formation. But whereas the asteroid belt is a disk of rocky fragments, we think the Kuiper Belt is made up of icy objects, with methane, water, and ammonia the major ingredients. And it's that list of ingredients that leads us back to Triton and its strange history. We believe now that perhaps only Triton grew up out in the Kuiper Belt, amongst the millions of other frozen lumps of water, ammonia, and methane circling the Sun, before something such as a collision disturbed its orbit and flung it inwards. Plucked from the Kuiper Belt, Triton would be captured by the gravitational pull of Neptune and forever trapped in its strange orbit around the blue planet. Today, Triton orbits in a nice regular circle around Neptune, a bit like the way that our moon orbits around the Earth. But to begin with, this newly captured satellite would have almost certainly been in a chaotic orbit. Glancing past the planet, it would have started along a wide elliptical path around Neptune, bringing it from far out to close in on every revolution. This would have meant that as Triton orbited Neptune, the gravitational pull would be constantly changing, stretching and squashing the moon, just as Jupiter does to Io today, with the result that the friction of these tidal forces would have heated up the interior of Triton, creating far more activity than the erupting geysers we see today. Through this process of tidal heating, the ancient interior of ice would have become molten and volatile, exploding up through cracks and faults in the moon's crust, creating the ragged surface we see today. Over time, as the orbit adjusted into a more regular circular path, the friction reduced, the heating diminished, and so what we're left with is an icy, frozen moon circling the wrong way around its planet, the subtle scars of its early life written across its surface. All that remains today of that dramatic, violent past are the geysers, powered by the faint light of the sun, painting dark streaks across the now quiescent surface. As Voyager 2 sped away from Triton and Neptune at over 60,000 kilometers per hour, the planetary exploration phase of this extraordinary mission finally came to an end. Its exploration would continue beyond even the furthest reaches of our solar system, and would extend into the unknown depths of interstellar space. But its time as a planetary explorer was over. A tiny spacecraft, built with 1,000 human hands, had shone a light into the darkness, revealing the secrets of worlds that had been hidden in the night for over 4 billion years. As yet, we have not returned. But while Neptune and Uranus have fallen back into the distance, viewed only through the lenses of our most powerful telescopes, another, even more distant world was out there waiting for our first arrival. On the night of the 23rd of January 1930, a 23-year-old junior researcher at the Lowell Observatory in Flagstaff, Arizona, took an image of the night sky using a 13-inch astrograph, a telescope designed for the sole purpose of astrophotography. Clyde Tombaugh had been at the observatory for just over a year when he took the image, one of hundreds he had captured over previous months. A keen amateur astronomer, he had landed this first job after sending in a series of drawings he had made of Jupiter and Mars using telescopes he had built at his home. Every night at the Lowell, Tombaugh performed the same task, using the astrograph to photograph a precise section of sky that he would then image again a few nights later. The task was a little laborious, but its purpose was profound, because hiding within the near-identical images, Tombaugh was on the hunt for a new world, the enigmatic Planet X. Unless we think hard, our intellects are confined to the surface of the Earth. After sunset, beyond cities, the universe appears, a destination for the imagination, albeit separated by a seemingly unbridgeable gulf. This may be true for the stars, but it is not so for the planets. There are times when Mars, Venus, Jupiter, and Saturn dominate the sky, bright lights that shift position nightly against the fixed stars, commanding our attention even if we aren't certain what we're looking at. The distances are still vast by terrestrial standards, but despite appearances, the gulf is certainly not unbridgeable, because we have visited all of these planets and taken our first steps into the outer reaches of the solar system and beyond. And yet the wandering lights in the dark still feel detached from human affairs, and the time and effort we've spent in visiting them might seem to be an indulgence. This assumption, however, is profoundly wrong. The solar system is a system. The Sun and the 8 major planets and countless billions of minor planets, moons, asteroids, comets, and unclassified lumps of ice and rock were formed back in the mists of time, and they continue to evolve as one. We rarely notice the dynamic, interconnected nature of our system, although asteroid strikes on our planet are not such a rare occurrence. The Chelyabinsk impact in February 2013 injured 1,500 people when a 12,000-ton asteroid broke up as it entered the Earth's atmosphere at 60 times the speed of sound. And the Tunguska airburst in Siberia in 1908 flattened 800 square miles of forest in an explosion comparable to that of the most powerful hydrogen bomb ever tested. The surface of the moon bears testament to a record of violence and destruction from the skies that the Earth has also endured. But the relentless erasure of craters by weathering, and our good fortune that no major impacts have occurred in recorded human history, are the reason for our misplaced sense of isolation from the heavens. The interdependent nature of the solar system has become more evident as we've begun to understand its history. It's tempting to imagine that the physical layout of the planets is a fossilized remnant of primordial patterns in the collapsing dust cloud around the newly ignited sun 4.6 billion years ago. But our exploration of the planets, coupled with increasingly powerful computer simulations of the evolution of the solar system.
Big Tobacco lied for decades about the dangers of secondhand smoke. Legally, here's what tobacco companies are forced to say now. Here's what they're really saying. Get the truth behind the lies at StopsWithMe.com, a program of TSET.
Ambition is what drives us forward. When you're eager to take your next step, MidFirst Bank helps guide you toward your bigger goals, so you can engage in your true passion. MidFirst Bank, true to your money.
Has revealed that this is not the case. Planetary orbits are prone to instability, particularly so in the early, more chaotic years when our solar system was young. The details of precisely how the planetary orbits have shifted are still uncertain, But we now suspect that Mercury, the innermost planet, began life much further out and was deflected inwards to its present-day seared orbit. Jupiter and Saturn may have drifted inwards shortly after their formation, before reversing their course and retreating, but not before affecting the distribution of material out of which Mars and Earth would later form. Around the time that life began on Earth, Neptune and Uranus may have been flung outwards, disrupting the orbits of billions of smaller objects far from the Sun. The record of this time of unprecedented violence, known as the Late Heavy Bombardment, is written across the scarred surface of the Moon, itself most likely formed in a glancing interplanetary collision between Earth and a Mars-sized planet 4.5 billion years ago. The planets are like snowflakes. The detail of their structure, their composition, size, spin, and climate are a frozen record of their past. An understanding of the planets beyond Earth is therefore a prerequisite for understanding our home world, and that, in turn, is a prerequisite for understanding ourselves. Earth is unique in the solar system because it's a planet with a complex ecosystem. The genesis and subsequent 4 billion year evolution of life on Earth required planetary characteristics which are necessarily linked to the evolution of the system as a whole. There had to be liquid water on the surface, and much of this water was delivered after the Earth's formation by icy, water-rich asteroids and comets, possibly deflected inwards from the outer solar system by Jupiter. These rivers, seas, and lakes of extraterrestrial origin had to persist for the best part of 4 billion years, which required a stable atmosphere to maintain surface temperatures and pressures within a limited range. 4 billion years is a long time, around a third of the age of the universe. The Sun has brightened by 25% since the Earth formed, which makes the stability of our environment all the more difficult to understand. In a chaotic system of planets around an evolving star, a planet with life-supporting properties and the remarkable stability enjoyed by Earth over billions of years may be extremely unusual. The study of our sister worlds, Mars and Venus, has proved instructive in understanding just how fortunate we may have been and how delicate our position today might be. 4 billion years ago, as life began on Earth, Mars was also Earth-like. It had oceans and rivers, and active geology and complex surface chemistry, the ingredients of life. One of the primary goals of the fleet of spacecraft currently in orbit around and exploring the surface of Mars is to search for evidence of past or even present life, and to understand why the red planet was transformed from a potential Eden at the dawn of the solar system to the frigid desert world we observe today. The story is complex, but one of the most important differences between the two worlds is size. Mars is just 1/10 the mass of Earth, too small to hang on to its internal heat, its protective magnetic field, and its atmosphere for much more than 1 billion years after its formation. Yet Mars formed in a similar region of the solar system to Earth and Venus, so why is it so small? The answer may lie in the fast-changing orbits of Jupiter and Saturn early in the solar system's history. The history of Venus is perhaps even more puzzling, in part because of the immense difficulty of exploring the planet. Venus is often described as a vision of hell. Surface temperatures are high enough to melt lead, and the atmospheric pressure is 90 times that on Earth. Sulfuric acid raindrops fall from its clouds. And yet, long ago, Venus too may have been Earth-like. Perhaps there were once Venusians, before a runaway greenhouse effect took hold and began destroying Venus's temperate climate about 2.5 billion years ago, although this date is highly uncertain. Taken together, the stories of the 3 large terrestrial planets are salutary. If an alien astronomer observed our solar system from afar, they would classify Mars, Earth, and Venus as potentially living worlds, orbiting as they do inside the so-called habitable zone around the Sun, the region within which, if atmospheric conditions are right, liquid water can exist on the surface of the planets. All 3 worlds may once have been habitable, and all 3 worlds may once have harbored life, But now only Earth supports a complex ecosystem, let alone a civilization. Understanding why Mars and Venus diverged so significantly from Earth over the last 4 billion years will provide great insight into the fragility of worlds, and perhaps suggest whether our own good fortune is near impossible to comprehend or merely outrageous. Planets change. Ours could change at any moment. A stray comet from the frozen Kuiper belt beyond the orbit of Neptune could put an end to our story. We could also put an end to ourselves. The study of Venus might help us avoid one of the ways by which we could destroy our civilization, because it shows us what greenhouse gases can do to a world. I think one of the reasons why anthropogenic climate change is so difficult for a certain type of person to accept is that atmospheres seem ethereal and tenuous, and incapable of trapping enough heat to modify the temperatures on a planet significantly. For such people, I suggest a trip to Venus, where they will be squashed and boiled and dissolved on the surface of Earth's twin. The exploration of the planets, then, is not an indulgence. If we want to know how we came to be here, we need to understand the histories of the planet that gave birth to us, and the system that gave birth to it. We are children of Earth, and also children of the solar system. Understanding our history is important because it places our existence in context. The more we learn about the events that led to the emergence of humans on this planet only a few 100,000 years ago, the more we are forced to marvel at the sheer unlikeliness of it all. We needed Jupiter and the comets and asteroids and countless collisions and mergers and near catastrophes stretching back 4.6 billion years. There are valid objections to this way of thinking. It is an objective fact that we are here, and our future should be our primary concern. That may be so, but I argue that a deeper understanding of the evolution of the planets is essential for our continued prosperity and existence on this one. The threat of catastrophic climate change is an obvious example, but there are many other reasons why knowledge is important. There is feedback in human affairs. Our collective state of mind affects the decisions we make. To confine our imaginations to the surface of the Earth is to ignore both our immense good fortune and the fragility of our position. A wider knowledge of both will, I believe, help secure a safer and more prosperous future. Earth sits a mere 150 million kilometers from the Sun. Not too hot, not too cold. With surface temperatures ranging from -88 to +58 degrees Celsius. This Goldilocks location has created a stability of climate that, despite the best efforts of ice ages and impacts, has allowed life to maintain an unbroken chain for nearly 4 billion years. And yet we know for certain that it cannot last. Our Sun, like every star in the universe, is far from static. Stars have life cycles of their own, and eventually the hydrogen fuel that powers the nuclear reactions within a star will begin to run out, and the star will enter the final phases of its lifetime. It will expand, cool, and change color to become a red giant. Small stars, like our Sun, will undergo a relatively peaceful and beautiful death, which will see it pass through a planetary nebula phase to become a white dwarf, which will cool down over time to leave a brown dwarf. Life on Earth has prospered through our Sun's middle years, but these optimum conditions are waning.
Kroger's professional drivers always deliver. Get $15 off your first 3 orders.
At first, the changes will be invisible, but 1 billion years from now, they will be obvious to any life forms left on the planet. An immense sun filling the sky will warm and transform itself and the Earth that it shines upon. The sun is both the giver and the taker of life on our planet. It is one of the great paradoxes of the universe that as the life of a star like ours begins to wane, its size and luminosity will increase. A rise in luminosity of just 10% will see the average surface temperature on Earth rise to 47 degrees Celsius instead of the 15 degrees Celsius that it is today. The effect of this rise in temperature manifests in a lifting of vast amounts of water vapor from the oceans into the atmosphere, creating a greenhouse effect that could quickly and rapidly run out of control, evaporating the oceans and sending the surface temperature skyrocketing. Astrobiologist David Grinspoon explains. The greenhouse effect is the name we give to the physical process by which planets heat up through the interaction of their atmospheres and solar radiation. Basically, solar radiation comes in what we call the visible wavelengths. Primarily, they're wavelengths that we can see, and most atmospheric gases are very transparent to visible radiation. So light from the sun comes through pretty much